Close your eyes. Let your body settle. Let the weight of everything you carried today begin to soften and dissolve into the mattress beneath you. You don't need to hold anything right now. The night is long and quiet, and I have a story to tell you. A very old story, told very slowly, about the stars above you and the way they live and breathe and eventually gently let go. Let my voice carry you. Let the darkness be soft around you. And just breathe. Every star in the universe has a lifespan. Just like you, just like every living thing you have ever loved or noticed or passed on the street, every single star that burns in the sky above you was born, and it lives, and one day it will die. This is not a sad thing. It is simply the nature of things, the long and patient rhythm of the universe going about its work. When you look up at the night sky on a clear evening, every point of light you see is a sun, some smaller than ours, some unimaginably larger, some young and restless and blazing blue-white with the energy of their youth, and some old and slow and amber-colored, burning their last long reserves with a patience that makes human lifetimes feel like the blink of an eye. And all of them, every single one, is somewhere in the middle of its own story. Some are near the beginning, newly ignited from collapsing clouds of gas and dust, just finding their rhythm. Some are in the long and stable middle of their lives, burning steadily the way our own sun burns today, reliable and warm and seemingly permanent. And some are near the end. Some are in the slow final chapters of a story that began billions of years ago. Tonight, we are going to follow one of them. One old and beautiful star, near the end of everything. Just breathe and let the story begin. The death of a star is not a sudden thing. It does not go out like a candle in a draft, snuffed in an instant, there one moment and gone the next. The death of a star is slow in a way that is almost impossible to hold in the human mind. Slow in the way that mountains are slow, slow in the way that continents are slow, only even slower than that. We are talking about processes that unfold over millions of years, sometimes billions, each stage easing gently into the next, the way one season eases into another. Not on a single day, but so gradually that you only notice the change when you look back and realize the leaves are all gone, or the snow has melted, or the light is staying later in the evenings than it was before. A star's death has stages, and each stage is its own kind of beauty. There is the swelling, when the star expands outward into a vast and reddened giant. There is the shedding, when the outer layers drift away into space like the petals of a flower releasing themselves to the wind. There is the remnant, the small, dense heart left behind at the center of it all, still glowing, still warm, still giving off light long after the burning has ended. And then there's the cooling, the long, slow cooling that takes longer than the universe has yet existed. None of it is rushed, none of it is hurried. The universe has plenty of time and it uses all of it. Let your own breathing slow now. There is no rush tonight. A star lives because of a process called nuclear fusion. This is the engine at the center of everything, the reason stars shine, the reason there is light and warmth and life in the universe at all. Deep in the core of a star, where temperatures reach tens of millions of degrees, and the pressure is so immense that it is beyond any human scale of comparison, hydrogen atoms are squeezed so tightly together that they fuse. They merge, two becoming one, releasing a burst of energy in the process. This energy is what we see when we look at the sun, what we feel on our skin on a warm afternoon, what makes plants grow and seasons turn and oceans stay liquid. It is the light that has traveled 93 million miles across empty space to fall through your window in the morning. And it all comes from this one simple, ancient process, hydrogen fusing into helium, over and over and over again, billions of times per second, in the core of every star that burns. A star is essentially a very long, very controlled explosion. Gravity pulling everything inward, fusion pushing energy outward, the two forces holding each other in a balance that can last for billions of years. While that balance holds, the star shines. Steady, reliable, warm. The way a campfire holds its shape while the wood lasts, giving heat and light to everything around it. Let that warmth reach you now. Let it settle over you like a blanket. But the fuel does not last forever. Nothing does. The hydrogen at the core of a star, vast as it is a finite supply, and over billions of years of continuous burning, it is gradually used up. This is the slow beginning of the end. Not a crisis, not a catastrophe, just the natural consequence of a fire that has been burning for a very long time. As the hydrogen in the core runs low, the fusion reactions begin to slow. The outward pressure they have been generating, the pressure that has been holding the star's own gravity at bay all this time, begins to weaken, and gravity, patient as it always is, begins to win. The core starts to contract, to squeeze inward under its own weight, growing hotter and denser as it compresses. And as it does, something interesting happens to the outer layers of the star. All that extra energy from the contracting core flows outward, and the outer layers begin to expand in response. The star grows larger. Slowly, over millions of years, it begins to swell. The surface cools as it stretches thinner, shifting from the bright white or yellow of its middle years to a deeper, warmer orange, and then to red. The star is becoming something different now. It is entering one of the most dramatic transformations in the universe. But tonight, we approach it gently. We approach it the way you approach the edge of sleep. Slowly, without forcing anything, letting the change come on its own. The outer layers of a star expand outward during the red giant phase. As they do, the star grows to sizes that are almost incomprehensible. Our own sun, in about 5 billion years, will swell outward to perhaps 100 times its current diameter. 100 times. If you tried to imagine something 100 times larger than something else, your mind might reach for something like a marble compared to a basketball. But a basketball compared to a marble is only about 10 times larger. We are talking about something far more vast than that. The sun, in its red giant phase, will stretch outward past the orbit of Mercury, past the orbit of Venus, possibly to the orbit of Earth itself, though by that point, the Earth will have long since been rendered uninhabitable, its oceans boiled away and its atmosphere stripped by the expanding star's heat. The inner solar system will be swallowed whole. And yet, the surface of the red giant will feel cooler than the sun does today because all that energy is spread across a surface so much larger. Red giants glow with a deep, warm redness, the color of coals in a dying fire, of autumn leaves in the last afternoon light, of the sky just after sunset when the day has not quite decided to give way to night. It is a mellow, ancient light, the light of something old and large and slow, burning its last long chapters with a kind of quiet dignity. Picture that color now behind your closed eyes, that warm, deep red. Our own sun will become a red giant someday. This is worth sitting with for a moment, not with anxiety, but with a kind of quiet wonder. 5,000 million years. To put that in perspective, the Earth itself is only about 4.5 billion years old. The entirety of life on this planet, every bacterium, every fern, every dinosaur, every human being who ever lived and loved and looked up at the stars, fits inside a span of time that is slightly shorter than the time remaining before our sun begins its expansion. We are, in the long story of the solar system, still quite early. The middle chapters are still being written. The sun today is a middle-aged star, stable and steady, content in its long equilibrium of fusion and gravity. It will burn this way for another 5 billion years before the hydrogen in its core runs short. And then, slowly, over tens of millions of years, it will begin to change. It will swell. It will redden. It will become something larger and stranger and more beautiful than anything our descendants, if they exist, will ever have seen before. But that is so far away that it has no bearing on tonight. Tonight the sun has already set, and the sky is dark, and you are warm in your bed, and all is well. Let your body be heavy. Let your mind go quiet. In stars more massive than our sun, the story moves faster. These massive stars burn their hydrogen far more quickly, living bright and furious lives that last only a few million years, instead of billions. They are the brilliant blue-white stars you sometimes see in the night sky, the ones that outshine everything around them. They burn so hot, so intensely, that they consume their fuel at a rate that would astonish you. And when the hydrogen runs out, they do not simply swell into red giants and then gently shed their layers. They continue fusing. The core gets hot enough to fuse helium into carbon, then carbon into oxygen, then oxygen into neon, neon into silicon, silicon into iron. Each stage happens faster than the last. Hydrogen burning takes millions of years, but silicon burning, the last stage before iron, takes only days. Days, in the life of a star that has existed for millions of years. It is like a long, slow exhale that suddenly becomes very fast at the very end. The star rushes through its final fuel supplies in a breathless sprint toward the inevitable. And then it reaches iron, and everything changes. But we are not there yet. For now, let the story stay gentle. Let it stay slow. Let your breathing match the pace of the telling. Unhurried, even. Soft. Iron is where the fusion story ends. Every element up to iron in the periodic table can be fused to release energy. Hydrogen to helium, helium to carbon, all the way up through the elements. Each fusion reaction giving off a burst of heat and light that helps hold the star against its own gravity. But iron is different. Iron sits at the bottom of the nuclear energy curve. To fuse iron into anything heavier requires putting energy in, not taking energy out. Iron cannot be burned. It simply accumulates in the core of a massive star like ash, building up in a fireplace. And unlike the ash in a fireplace, it cannot be swept away. It sits there, growing heavier and denser, until the core becomes a sphere of iron the size of a small planet, compressed to unimaginable density by the weight of the entire star above it. And then, when the iron core reaches a critical mass, when gravity finally overwhelms the last resistance, the core collapses. In less than a second, the entire iron core, hundreds of thousands of miles across, implodes to a sphere about 12 miles in diameter. The collapse is so fast, so violent, that it generates a shockwave that blasts outward through the rest of the star, and the star explodes. But that is the story of the most massive stars. For a star like the one we are following tonight, a gentler star, a quieter one, the ending is softer, much softer. The way sleep comes on a quiet night, without drama, without suddenness, simply arriving. For a star like our Sun, after the red giant phase, something very beautiful happens. The star does not explode. It breathes out. Over thousands and thousands of years, the outer layers of the star are gently expelled into space, pushed outward by radiation pressure and stellar winds, drifting away from the core in great slow shells of gas and dust. These expanding clouds of material surround the dying star's core like a series of concentric veils, each one thinner and more transparent than the last. Each one lit from within by the ultraviolet radiation still streaming from the hot exposed core at the center. Astronomers call these structures planetary nebulae, a name that was given to them centuries ago when early telescopes made them look soft and round, somewhat like the disk of a planet. They have nothing to do with planets, really. They are something far more extraordinary. They are the outer layers of a dead star, dispersing into space, glowing with the last energy their sun can give them. They are, in a very real sense, the star's last breath, a slow, expansive, luminous exhalation into the void. Breathe out slowly now. Feel your own chest settle, your own breath moving outward, quiet and natural, the way everything in the universe eventually releases what it has been holding. Planetary nebulae are among the most visually stunning objects in the entire universe. If you have ever seen a photograph from a space telescope, the kind that shows clouds of gas in impossible colors, rings and loops and intricate structures of light against the blackness of space, there is a good chance you are looking at a planetary nebula. They come in every shape, perfect rings like smoke rings blown by some enormous mouth, spheres within spheres, layer after layer of glowing gas, butterfly shapes, where the gas has been expelled preferentially along two opposite directions, creating great wings of luminous material stretching across light years, hourglass shapes, and helical shapes, and shapes that have no name yet because no one has seen anything quite like them before. Each one is unique. Each one is the particular signature of one particular star, expressing in its final dispersal all the idiosyncrasies of its own mass and rotation and magnetic field. They are as individual as faces, as unrepeatable as snowflakes, and they glow in colors that take the breath away, pale blue at the very edges where the gas is thin and the ionization is gentle, deepening to blue-green in the denser regions where oxygen glows, shifting to gold and amber where the light begins to cool, and at the very heart of things, a deep and burning crimson where hydrogen recombines and releases its soft red light. Imagine those colors now, in the darkness behind your eyes. Soft, luminous, slowly turning. The colors of a planetary nebula are not random. They are the specific signatures of specific atoms, each element releasing light at its own particular wavelength when it is energized by the radiation from the star at the nebula's center. Hydrogen, the most abundant element in the universe, glows in a deep reddish pink when its electrons are excited and then settle back down. This is the color that dominates the outer edges of many nebulae, a warm and familiar red. Oxygen, when it is doubly ionized, glows in a striking blue-green, a color so characteristic of planetary nebulae that astronomers sometimes call it the nebular green. Nitrogen glows red. Sulfur glows deep red and orange. Helium glows blue. And when all these colors mix together, when you have layers and zones of different temperatures and densities and compositions all glowing at once, the result is something that looks almost painted, vivid, and layered and full of depth, like a piece of art that the universe made slowly over thousands of years, using only light and gas and gravity. Every nebula is a painting. Every dying star leaves behind a canvas. And the remarkable thing is that these colors are not just beautiful, they are informative. Each color tells astronomers something about what the star was made of, how hot it burned, how fast it was spinning. The colors are a record, a legacy, the star's last words, written in light across the fabric of space. At the center of every planetary nebula, there is a tiny and intensely hot remnant, the exposed core of the dead star, all its outer layers now drifted away, compressed by gravity into something new and extraordinary. This is what astronomers call a white dwarf. It is small, compared to what the star once was, roughly the size of the Earth. Which sounds significant until you remember that the star it came from was perhaps 1,000,000 times the volume of the Earth, and in its red giant phase, perhaps 1,000,000,000 times. What is left is a tiny, dense ember, a cinder, but do not let its size fool you. A white dwarf contains most of the mass of the original star, compressed into that small volume. A teaspoon of white dwarf material, if you could somehow bring it to Earth, would weigh tons. The gravity at its surface is hundreds of thousands of times stronger than the gravity you are feeling right now, lying in your bed. It is, in the language of physics, a degenerate object, meaning that it is supported against further collapse, not by thermal pressure or fusion, but by a quantum mechanical force called electron degeneracy pressure, which is simply the resistance of electrons to being compressed too closely together. The star has found a new equilibrium, a new stillness. It has stopped burning, but it has not yet gone out. Let that image sit with you, a small, still incredibly dense point of warmth in the dark, glowing without effort, simply radiating what it holds. A white dwarf is roughly the size of Earth. This comparison is worth sitting with gently for a moment. The Earth, which feels so impossibly large when you are standing on it, when you think about all the oceans, all the mountain ranges, all the cities and forests and deserts and ice caps, is by cosmic standards a rather small thing. Our sun could fit about 1,000,000 Earths inside it, and yet here is a dead star, a remnant that once was a sun, compressed down to that same modest size. The compression is almost beyond imagining, and yet in other ways, a white dwarf is surprisingly quiet. It does not pulse like a neutron star. It does not emit jets of radiation or send out shockwaves. It simply sits there, dense and still, radiating the heat it has stored the way a stone radiates warmth after a long day in the sun. The outer surface of a newly formed white dwarf can be extraordinarily hot, temperatures of 50,000 degrees or more, hot enough to emit significant ultraviolet radiation, which is what powers the glow of the nebula surrounding it. But over time, over millions and then billions of years, it cools, slowly, steadily, the way a coal cools after the fire has been put out, keeping its warmth for a long time before it finally becomes cold and dark. Let yourself be warm now. Let the warmth hold you. The nebula that surrounds the white dwarf is constantly changing, though so slowly that no human lifetime could perceive the change. The gas continues to drift outward at a few kilometers per second, which sounds fast, but across the scale of space is barely a whisper. The innermost shells glow most brightly, where the gas is still dense enough to hold the light. The outermost shells have thinned to near invisibility, a faint tracery of luminescence at the very edge of the structure. transparent as gauze. Over thousands of years, the nebula expands and thins, the colors shifting as the white dwarf cools and emits less energetic radiation. The bright blues and greens fade first. As the ultraviolet light weakens, the reds linger longest, hydrogen's soft glow persisting even as the other colors dim. Eventually, after perhaps 10 or 20,000 years, the nebula has expanded so far and thinned so much that it becomes invisible, its atoms too widely spaced to catch enough light, too diffuse to hold their color against the darkness of space. The nebula disperses. The show is over. What remains is just the white dwarf, alone at the center of empty space, still glowing, still warm, but no longer wearing its beautiful shroud of color. The way a celebration ends, and the guests go home, and the lights are put out one by one, and all that remains is the quiet of the house, and the warmth, and the memory of something beautiful. Your eyes are heavy now. Let them stay closed. The gas and dust expelled by a dying star does not simply vanish into nothing. The universe does not work that way. Nothing is lost. The atoms that made up the outer layers of that star, the hydrogen and helium and carbon and oxygen and nitrogen, drift outward into the broader medium of the galaxy, mixing with the vast clouds of gas and dust that occupy the spaces between the stars. These clouds are the raw material of the universe's next generation of suns and planets. They are the nurseries where new stars are being made, even as old ones die. When a sufficiently dense region of one of these clouds collapses under its own gravity, triggered perhaps by a nearby supernova, or the passage of a spiral arm, or simply the slow accumulation of enough material in one place, a new star begins to form. And that new star will be made partly of the material from older stars. It will inherit the carbon that was forged in the cores of red giants that burned and died before the sun was born. It will carry within it traces of all the stellar generations that came before. The universe recycles itself endlessly and generously, using the material from each generation of stars to build the next. Nothing is wasted. Everything is transformed. The atoms find new homes, new configurations, new stories. This is one of the deepest and most comforting truths about the universe, that it keeps everything, that nothing is truly lost, that every ending carries within it the seeds of something new. Almost every heavy element in the universe was made inside a star. This is a fact that astronomers and physicists worked out over many decades of careful observation and calculation, and it is one of the most profound discoveries in the history of science. The hydrogen and helium that emerged from the Big Bang were almost the only elements in the early universe. Two simple building blocks, abundant and light, but not yet enough to make anything complicated. It was only inside stars, in the enormous temperatures and pressures of stellar cores, that heavier elements were forged. Carbon, the backbone of all organic chemistry, was made by helium fusion in the cores of red giants. Oxygen, the most abundant element in the Earth's crust, was forged in the later stages of stellar evolution. The iron in your blood was made in the core of a massive star that exploded as a supernova billions of years ago. The calcium in your bones, the nitrogen in your DNA, the oxygen in every breath you take, all of it came from stars. All of it was made in the furnaces of suns that lived and died before our solar system existed. You are, in the most literal and physical sense, made of stellar material. The universe built you from the inside out, using the elements that dying stars scattered into space. You are not separate from the cosmos. You are part of it. You are made of it. Let that settle into you now, gently, as you lie in the dark. You are the universe looking at itself. And tonight, you are resting. We are all made of star stuff. This is one of the most beautiful phrases in all of science. A phrase so simply true that it feels like poetry, because it is. The atoms in your body have a history so long and so strange that no story could fully contain it. The carbon atoms in your cells were fused in the core of a red giant that lived and died before our solar system existed. They were expelled in a planetary nebula, drifting through space for millions of years. They were swept up in the cloud of gas and dust that eventually collapsed to form our sun and its planets. They settled into the young Earth, were incorporated into rocks and oceans, were taken up by the first living things, passed from organism to organism through billions of years of evolution, and eventually, after a journey so long it strains the imagination, they arrived in you, in your hands. in your lungs, in the neurons firing softly in your brain right now as you listen to this story and feel the weight of sleep beginning to gather at the edges of your awareness. You are the latest chapter in a story that began in the heart of a star. Let that be enough for tonight. Let that be more than enough. Let us return now to the white dwarf at the center of our story, sitting quietly in the space where its nebula used to be. The nebula has long since dispersed. The colors have faded. The gas has moved on to join the broader medium of the galaxy. What remains is just this small, dense sphere, glowing white against the black. It does not burn. There is nothing left to burn. But it is not cold. It is still immensely hot, carrying within its compressed mass the thermal energy of billions of years of stellar burning, stored now in the motion of its tightly packed atoms, radiating slowly outward into the void. A white dwarf cools the way the last log in a fireplace cools after the flame is out. Slowly at first, still quite warm for a long time, the heat reluctant to leave. The universe is patient, and so is the white dwarf. It radiates its heat over timescales that dwarf even its own long life. A newly formed white dwarf might remain hot enough to glow visibly for hundreds of millions of years. Then, as it cools further, it shifts in color, white to yellow-white, yellow-white to pale yellow to orange, orange eventually to red. The light gets softer, redder, warmer in color even as the object itself grows colder. It is a long and gentle dimming, a slow and patient closing of the light. Your own eyes are heavy now. Your own light is dimming gently towards sleep. There is a theoretical end state for a white dwarf that no one has ever seen, because the universe has not yet been old enough to produce one. As a white dwarf cools, over hundreds of billions of years, it should eventually cool to black. A cold, dark, dense sphere of carbon and oxygen, invisible against the stars, still there but no longer announcing itself with any light. This is called a black dwarf. But here is the remarkable thing. The universe is only about 13.8 billion years old, and the time required for a white dwarf to cool to black is estimated to be far, far longer than that. On the order of many quadrillions of years, a number so large it has no practical meaning in human experience. Which means that right now, in this moment of cosmic history, there are no black dwarfs anywhere in the universe. Every white dwarf that has ever formed is still glowing. Every one of them is still radiating, still warm, still holding its light. The universe is not yet old enough for its stars to have truly gone out. All the dead stars are still there, still glowing, still releasing their stored heat into the dark. Dimmer than they were, but present. Still present. There is something quietly wonderful in that. The universe has not yet allowed any of its stars to be truly dark. Not yet. For the most massive stars, the ending is one of the most violent events in the universe. When the iron core of a massive star collapses, it does so in less than a second, and the energy released in that collapse is staggering. More energy in that fraction of a second than our sun will release in its entire 10 billion year lifetime. The shock wave that blasts outward through the star tears the entire stellar body apart in an explosion called a supernova. For a brief period, days or weeks, the supernova can outshine its entire host galaxy, a single dying star blazing as brightly as 100 billion suns combined. If a star in our own galaxy were to go supernova close enough, we would be able to see it in daylight. We would see a new star appear in the sky, bright enough to read by at night, fading slowly over weeks and months as the explosion dispersed. Historical records describe exactly this. Bright new stars appearing in the sky and fading, recorded by astronomers in China and the Arab world. In medieval Europe, they were watching stars die. They were seeing light that had been traveling for thousands of years, arriving at last at Earth in one final brilliant announcement. Sleep now. The explosions are very far away. After a supernova, the stellar material blasted outward forms a supernova remnant, a vast and turbulent cloud of gas and dust, lit from within by the energy of the explosion, expanding outward at thousands of kilometers per second. These remnants are beautiful in their own wild way, quite different from the soft and luminous planetary nebulae of smaller stars, where a planetary nebula is gentle and symmetrical. A supernova remnant is ragged and complex, wisps and filaments and knots of glowing material. tangled and dynamic, still carrying the memory of the violence that created them. The Crab Nebula, one of the most famous objects in the sky, is a supernova remnant, the remains of a star that exploded in the year 1054, observed by Chinese astronomers who recorded the appearance of a brilliant new star in the constellation we now call Taurus. That explosion happened 6,500 light-years away, which means the light that reached Earth in 1054 had actually been traveling since long before human civilization existed. And today, nearly 1,000 years after that light arrived, the nebula is still expanding, still glowing, still carrying the energy of a star that died 6,500 years ago. The universe keeps records. It does not forget. And neither do we. At the center of a supernova remnant, something extraordinary remains. When the core implodes, the protons and electrons of the iron atoms are squeezed together with such force that they combine, forming neutrons, and the result is an object composed almost entirely of neutrons, packed together as tightly as the nucleus of an atom. This is a neutron star, and it is one of the strangest objects in the known universe. A neutron star is about 12 miles across, about the size of a city. You could drive across it on a highway in perhaps 15 minutes, and yet it contains more mass than our sun. A teaspoon of neutron star material would weigh something like 1 billion tons. The gravity at its surface is 200 billion times stronger than Earth's gravity. Time itself runs measurably slower there, bent by the extreme curvature of space-time that such a concentration of mass creates. If you were somehow standing on its surface, which is not possible for many reasons, you would be crushed to a layer thinner than an atom in less than a millisecond. And yet, neutron stars are real. They exist. There are hundreds of millions of them in our galaxy, floating in the dark, the remnants of stars that died in fire, cold and small and impossibly dense. Orbiting the galaxy in silence. Lie very still now. Let the silence hold you. Some neutron stars spin, and they are among the most precise objects in nature. When a star's core collapses to form a neutron star, the conservation of angular momentum, the same physical law that makes a spinning ice skater speed up when they pull in their arms, causes the neutron star to spin faster as it shrinks. A core that was rotating relatively slowly becomes a neutron star rotating many times per second. Some neutron stars spin hundreds of times per second, so fast that their surfaces are moving at a significant fraction of the speed of light. And as they spin, they emit beams of radio waves from their magnetic poles. Poles that are not aligned with their rotation axis. So the beams sweep around like the beam of a lighthouse. When one of these beams happens to point toward Earth as the neutron star rotates, we detect a pulse of radio waves, perfectly regular, perfectly timed, arriving with a precision that rivals atomic clocks. These objects are called pulsars, and when they were first discovered in 1967, the signals were so regular and so precise that the astronomers who found them initially thought they might be artificial. Signals from some other civilization, perhaps, reaching out across the dark. They even half-jokingly called the first discovery LGM-1 for little green men. But no, it was just a neutron star spinning in the dark, sweeping its beam across the galaxy with mechanical precision. Nature doing what it does, being strange and wonderful and indifferent to our amazement. The gas and dust expelled by dying stars seeds the next generation of stars. Eventually, it finds its way into new clouds of material drifting through the galaxy. And these clouds, given time and the right conditions, collapse to form new stars. This is the great cycle of stellar evolution, the universe endlessly transforming its material from one form to another, stars being born from the ashes of older stars, each generation enriched with the heavy elements forged by the ones that came before. The very first stars in the universe, born just a few 100 million years after the Big Bang, were composed entirely of hydrogen and helium. Nothing else existed yet. They were enormous stars, burning hot and fast. And when they died, they seeded the universe with its first carbon, its first oxygen, its first iron. The stars of the second generation were slightly richer in heavy elements, and each subsequent generation richer, still, as more and more supernovae and planetary nebulae added their contributions to the cosmic medium. Our own sun is a third-generation star, or perhaps even later. It formed from a cloud of gas that had already been enriched by many previous stellar generations. We are, in a very real sense, the children of all those earlier stars. Their legacy lives in the chemistry of every living cell on this planet. Let that lineage be a comfort to you tonight. Almost every heavy element beyond iron was forged in the most extreme cosmic events. The gold in jewelry, the silver in coins, the uranium in reactor fuel, the iodine in your thyroid gland, was made not in the steady burning of a star, but in the extreme conditions of a supernova, or in the collision of two neutron stars. These exotic environments are where the universe forges its rarest and heaviest elements, in a process called the R process, where atomic nuclei are bombarded with so many neutrons so quickly that they are forced to absorb them and build up into heavy exotic isotopes. In 2017, astronomers observed for the first time the collision of two neutron stars, two tiny, impossibly dense remnants of dead stars, orbiting each other and spiraling closer over millions of years until they finally merged in an event called a kilonova. The light from that merger, detected by gravitational wave detectors and optical telescopes, simultaneously showed clear signatures of heavy elements being forged in real time. Gold, platinum, the universe making its rarest treasures in the most violent collision imaginable. When you look at something gold, you are looking at an element that was forged in a neutron-star merger and scattered across space billions of years ago. You are holding a piece of an ancient cosmic event, quietly beautiful when you think about it that way. Let that beauty settle over you. The light from a dying star continues traveling through space long after the star itself is gone. This is one of the quiet marvels of the universe, and it is worth sitting with for a moment before sleep. Light travels at approximately 300,000 kilometers per second, a speed so great that it can circle the Earth 7 times in a single second. And yet the universe is so vast that even at this extraordinary speed, light takes enormous amounts of time to cross the distances involved. When you look at a star in the night sky, you are not seeing that star as it is now. You are seeing it as it was when the light you are receiving left it. For nearby stars, this might be a few years or a few decades. For stars in distant parts of our galaxy, it might be thousands of years. For stars in other galaxies, millions or billions of years. Some of the stars you can see with your naked eye, on a clear night, no longer exist. They died, swelled into red giants, shed their planetary nebulae, collapsed to white dwarfs, before the light now reaching your eyes had even finished its journey. You are looking at ghosts. The universe, in this sense, is a vast and beautiful archive of the past, preserving in light the record of everything that has happened, carrying those records across the dark at the only speed there is, delivering them eventually to any eye willing to look up and receive them. A dying star does not truly disappear. This is perhaps the most important thing to understand about all of this, and it is the thing that makes the whole story not sad but somehow deeply reassuring. The atoms of the star persist. They travel through space. They join new clouds. They collapse into new stars. They are forged into new planets. They become part of living things. The light the star emitted continues traveling outward in every direction, carrying its record of what the star was into the deepest reaches of the universe, never stopping, never fading to nothing, simply spreading thinner over larger and larger volumes of space. The gravitational influence the star had on its surroundings, the subtle perturbations it made in the orbits of things around it, the waves it sent through the fabric of space-time, those too persist, propagating outward at the speed of light. A star's death is not an erasure, it is a transformation, a dispersal. The way a river disperses when it reaches the sea, the river does not cease to exist, it simply becomes part of something larger. The water that was the river is now the ocean, and the atmosphere, and the rain that will fall on mountains and run in streams and eventually become a river again. Nothing is truly lost. Everything continues, in changed form, as part of something that was always larger than any individual thing. Let that be the last thought you hold tonight. Nothing is truly lost. The death of a star is in the end a generous act. Every element heavier than hydrogen and helium that exists in the universe was created inside a star and given to the universe by that star's death. Every red giant that shed its layers gave back its carbon and oxygen to the interstellar medium. Every supernova that detonated gave back its iron and nickel and silicon. Every neutron star merger that scattered its gold and platinum into space was a gift, an extravagant, violent, ultimately generous act of cosmic giving. The universe has been building up its chemical complexity for 13 billion years through exactly this process. Stars forming, burning, dying, giving back enriched material, forming new stars. Those stars burning and dying and giving back still more. The complexity keeps increasing. The chemistry keeps deepening. What began as a nearly featureless gas of hydrogen and helium has become, over billions of years and countless stellar generations, a universe rich enough to build planets, rich enough to build oceans and atmospheres and soils, rich enough to build living things, rich enough to build minds that can sit in bed on a quiet night and wonder about all of it. You are the result of 13 billion years of stellar generosity. You are what the universe has been building toward, through all that patient dying and giving and rebuilding. You are what it made when it had enough material to work with. And tonight, you are resting. Let yourself rest completely. The white dwarf glows on and will for longer than we can imagine. Cooling slowly, so slowly, shifting over billions of years from white to yellow to orange. A long and patient dimming. It is still there in the dark, still warm, still giving off its faint and steady light. Not gone, not forgotten. Simply changed. Simply continuing in a different form, at a different pace, with a different role in the great ongoing story of the universe. There is something deeply comforting about the persistence of a white dwarf. This small, dense, warm thing, sitting quietly in the dark, doing nothing dramatic, nothing violent, simply being present and warm, and gradually, gently dimming. It has no urgency, it has no agenda. It simply radiates what it holds, for as long as it holds it, and then it will cool, and then it will become something colder and darker. And through all of it, it will simply be there, in the dark, among the stars. The universe does not rush it. The universe lets it take all the time it needs. And you, lying here in the warmth of your bed, in the quiet of your room, the night gathered softly around you, you also do not need to rush. And so we come, gently, to the end of our story. The star we have been following has completed its long journey. Its outer layers drifted away into a beautiful nebula, glowing for thousands of years in rings of blue and green and gold and red, before dispersing into the galaxy. Its core collapsed into a white dwarf, dense and small and still hot, radiating its stored energy slowly into the void. The nebula has long since gone invisible, its atoms mixed into the broader medium of space, on their way to becoming parts of new clouds, new stars, new stories. The white dwarf glows on, cooling slowly, so slowly, shifting over billions of years from white to yellow to orange, a long and patient dimming. It is still there in the dark, still warm, still giving off its faint and steady light. Not gone, not forgotten, simply changed. Simply continuing in a different form, at a different pace, with a different role in the great ongoing story of the universe. The star did not fail. The star completed its purpose. It burned, and it gave light and heat to anything nearby, and it forged the elements that the universe needed, and it gave them back, and it rested. That is the whole of it. That is enough. You too have done what you came to do today. You too can rest now. The story is complete. The light is still traveling. The atoms are still moving. Everything is as it should be. Close your eyes. Breathe out. Sleep. The universe is patient. It is not finished with its work, and neither are you. Good night.